కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning, everyone. So in the previous classes, we already discussed about what is the definition of correlation, how it is defined, what is autocorrelation, what is cross correlation, what is the relation between autocorrelation and cross correlation. Okay, what is energy density spectrum, what is power density spectrum, what is Parseval's theorem. Okay, energy density spectrum is nothing but the Parseval's theorem, right? And what is the relation between energy density spectrum and correlation, relation between correlation and convolution. Okay, next, detection of the periodic signal in the presence of noise by using two techniques, correlation and filtering. Okay, we already discussed all these things in our earlier classes. Now we are going to discuss about the sampling theorem. What is meant by sampling theorem? And first of all, what is meant by sampling? What is meant by sampling? Sampling is nothing but it is the process of converting the continuous time signal into discrete time signal. Continuous time signal into discrete time signal. Okay? How to convert this continuous time signal into discrete time signal? So here the continuous time signal will take the sample of the continuous time signal. It can be frozen for some time and it can be divided into equal intervals of the time. That is called the process of sampling. Okay, sampling process is nothing but the continuous time signal can be frozen for some time and it can be divided into equal intervals of the time. Okay, some sample of the continuous time signal can be frozen for some time and it can be divided into equal intervals of the time. So it can be divided into equal intervals of the time is nothing but the discrete time signal. So continuous time signal can be converted into discrete time signal. It is nothing but the sampling process. So after the sampling, the signal is defined at discrete instants of time and the time interval between two subsequent sampling instants is called sampling interval. Sampling interval. What is meant by sampling interval? After the sampling, the signal is defined at discrete instants of time. Okay, the signal is defined at discrete instants of time, and the time interval between these subsequent sampling instants is called sampling interval. So continuous time period, in continuous time period also we have some time interval. So with that particular time period it will be repeated. That is in the case of the continuous time signal. Okay, what is the sampling interval in discrete time signal? So it is nothing but the distance between discrete instants of the time. It is the time interval between two subsequent sampling instants. That is called sampling interval. It is also like continuous time interval. Okay. So after sampling, the signal is defined at discrete instants of time, and the time interval between the subsequent sampling instants is called sampling interval. So here one of the important factors is signal sampling rate. Signal sampling rate must be kept sufficiently high. Signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. So, okay, so here the sinusoidal signal is the original signal. It can be converted into discrete time signal. From the discrete time signal, we can reconstruct the original signal, such that here the condition is the signal sampling rate must be sufficiently high. So this is one of the important factors in signal sampling. So the signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. So it is represented diagrammatically as, see here it is represented diagrammatically like this. See, x of t is the input signal, so it can be sampled so that it will become the discrete time signal x of n. X of t is the continuous time signal. X of n is the discrete time signal, or it is also represented as x of nt, that is sampled sequence of x of t. It is nothing but discrete time signal. Okay, so here it is also represented like this. Here the sinusoidal signal is multiplied with the impulse response delta t of t. This is the impulse response, so that it will become x of nt. So it will represent it like this. So here the continuous time signal can be divided into equal intervals of the time. So this is the discrete time signal having the equal intervals. So it can be frozen for, as we already discussed, as it can be a sample of a continuous time signal can be frozen for some time, and it can be divided into equal intervals of the time. That is called the sampling process. So it's represented diagrammatically as, here the continuous time signal x of t can be multiplied with the impulse response, train of impulses. Here these are the train of impulses. See here, these are the train delta t of t are train of impulses. So that the resultant will be the discrete time signal x of nt. Okay, so this is nothing but the diagram related to sampling operation, where capital T is the time interval between successive samples and the sampling frequency. Okay, successive samples. See here, these are the successive samples. Okay, so it is the time interval between successive samples, and the sampling frequency, that is fs, is given by reciprocal of the time interval t, that is 1 by t. Okay, fs equal to 1 by t h. So diagrammatically the sampling operation is represented like this. It is diagrammatically represented like this. Okay, this is the sampling operation. Okay, right. Another way of representing the discrete time signal is that is the diagram 2. That is excess of t is nothing but x of t, that is the input signal, which is multiplied with the train of impulses, that is delta t of t. That is equation number 1, where delta t of t is nothing but these are train of impulses represented from minus infinity to plus infinity. So it is represented like this: sigma n equal to minus infinity to infinity delta of t minus nt. That is treated as equation number 2. So it can be shifted towards right side or left side with the time interval t. Okay, that's why it is represented as delta t of t is equal to sigma n equal to minus infinity to infinity delta of t minus nt. That is equation number 2. So that is the function xs of t is the product of the input signal x of t and the train of impulses, that is xs of t equal to sigma n is minus infinity to infinity delta of t minus nt into x of t is represented as x of nt. That is equation number 3. Okay, so applying Fourier transform to equation number 3. So what is equation number 3? Xs of t is equal to sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. That's all. What is x of nt? X of nt is a sampled sequence of x of t, right? X of nt is sampled sequence of x of t. Okay, So that sample sequence of x of t multiplied with the train of impulses, that is sigma n equal to minus infinity to infinity x of t delta of t minus nt, delta of t minus nt. That is equation number 3. Now we are taking the Fourier transform for the equation number 3 on both sides. Okay, Fourier transform of xs of t is equal to Fourier transform of sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. So that is that is written as sigma n equal to minus infinity to infinity x of nt into Fourier transform delta of t minus nt. So here it is nothing but a frequency shifting property. So we have Fourier transform delta of t minus nt is delta of t minus nt in t power minus j omega t dt, right? So it is delta at t equal to nt, delta of t minus nt value is 1. That's why it will become e power minus j omega nt. Okay, e power minus j omega nt. That is equation number 5. Therefore, Fourier transform of this one, that is x of e power j omega is equal to Fourier transform of x of st is equal to xs of t is equal to sigma n equal to minus infinity to infinity x of nt into e power minus j omega nt. That is equation number 6. But we know that delta t of t is equal to sigma n is minus infinity to infinity delta of t minus nt, which has the equation 1 by t into sigma m equal to minus infinity to infinity e power jm omega naught t. So it is represented as 1 by t into sigma m equal to minus infinity to infinity e power jm omega naught t. That is equation number 7, where omega naught is equal to 2 pi by t. Okay, 2 pi by t or 2 pi f. Okay, omega naught is 2 pi f, right? So therefore xs of t is equal to x of t into delta t of t, that is 1 by t into sigma m equal to minus infinity to infinity e power jn omega naught t, or we can write this as 1 by t into sigma m equal to minus infinity to infinity x of t into e power jn omega naught t. That is equation number 8. So it is equal to 1 by t into sigma m is minus infinity to infinity f of Fourier transform of x of t into e power jm omega naught t. That is equation number 9. If Fourier transform of x of t is x of j omega, then Fourier transform of x of t into e power j omega naught t is x of j into omega minus omega. This is nothing but a time shifting property, right? Time shifting property. So by substituting equation number 10 in equation number 9, we get Fourier transform of xs of t is equal to 1 by t into sigma m equal to minus infinity to infinity. This Fourier transform of this entire thing can be replaced by capital X of j omega into j omega minus m omega naught. That is equation number 11. Or we can write this as 1 by t sigma m equal to minus infinity to infinity x of j omega minus m omega naught is nothing but 2 pi by t, 2 pi by t or 2 pi f. Okay, this is equation number 12. Thus, the Fourier transform of the sample signal, that is xs of t, is given by an infinite sum of shifted replicas of the Fourier transform of the original signal. Here, the same waveform shifted can be shifted with this parameter from minus infinity to plus infinity. Okay, so that is nothing but an infinite sum of shifted replicas of the Fourier transform of the original signal. Okay, so this is nothing but the representation of the discrete time signal, another way of representation of the discrete time signal. Okay, so what we have done here, So basic equation, that is excess of t sampled version of the signal x of t is excess of t, which is given by the product of the input signal and the train of impulses, that is x of sorry x of t, and the train of impulses are delta t of t. Okay, so that is represented as sigma n equal to minus infinity to infinity delta of t minus nt. That is equation number 2. Okay, so it is represented as x of nt into delta of t minus nt. That is equation number 3. Now we are taking the Fourier transform for equation number 3, so that it will become equation number 4 as a Fourier transform of x of t is equal to sigma n is minus infinity to infinity x of nt into Fourier transform delta of t minus n. Now we are taking the Fourier transform of delta of t minus nt, that will become e power minus j omega nt. So this will be replaced by e power minus j omega nt. But we know that train of impulses delta t of t are represented as sigma n equal to minus infinity to infinity delta of t minus nt, it is equal to 1 by t into sigma n equal to minus infinity to infinity e power jm omega naught t, where omega naught is 2 pi by t or 2 pi f. Okay, so replacing the value of e power jm omega naught t as e power jm 2 pi by t into t. Okay, so we can write this as a Fourier transform of excess of t as 1 by t into sigma n is minus infinity to infinity f of x of t into e power jm omega naught. This is nothing but the time shifting property of the Fourier transform, right? That is x of j omega minus m omega naught. So m can be replaced by omega naught can be replaced by 2 pi by t, so that it will become the equation number 12 as 1 by t into sigma m is minus infinity to infinity x of j of omega minus 2 pi by m by t. So it represents the Fourier transform of the sample filter signal is given by an infinite sum of shifted replicas of the Fourier transform of the original signal. Now consider the signal x of t is band limited to fm. Band limited to fm. Earlier we discussed about the x of t over the infinite interval. Okay, suppose if it is band limited to fm. Okay, that is it is represented in between minus fm to plus fm or minus omega m to plus omega m. Okay, so that is the highest frequency component of x of t is fm. Then x of j omega becomes 0 for mod omega is greater than omega m, where omega m is 2 pi fm. That is treated as equation number 13. Okay, so here we are limited. We are limiting the band. Okay, we are limiting the frequency, so that's why it is represented as band limited. So now we consider the signal x of t is band limited to fm. That is the highest frequency component of x of t is fm. Then x of j omega becomes 0 for mod omega is greater than omega m, where omega m is 2 pi into fm. So it is shown like this. The frequency spectrum of continuous time signal is represented like this. So this is the frequency spectrum located from minus omega m to plus omega m, and uh, and this is the frequency spectrum of x of and the sampled signal of x of t with the phi by t is omega m is represented like this. So it is xs of j omega and this is x of j omega, right? So it is represented. It is represented as a spectrum, frequency spectrum like this. It is from minus infinity to plus infinity. This is the basic continuous time signal spectrum, and this is a sampled signal, that is discrete time signals spectrum. This is the continuous time signals uh, frequency spectrum, and this is the discrete time signal frequency spectrum. Okay, right. This is the frequency spectrum of x of nt with phi by t is greater than omega n. Earlier one is phi by t is equal to omega n. If phi by t is equal to omega n, then this is represented like here. Here the waveform is represented like this. Suppose if phi by t is greater than omega n, there is a gap between these these peaks. So there is a gap between these peaks. If phi by t is greater than omega. Suppose if phi by t is less than omega n, so there is a overlapping of these peaks. Okay, so this is the overlapping area. So this is called aliasing. This is called aliasing. This is the uh, overlapping between the peaks. Then it is called aliasing. Here aliasing occurs when the phi by t, when the value of phi by t is less than omega m. If it is equal to omega m, there is no aliasing occurs. If it is greater than omega, pi by t is greater than omega, there is a gap between the peaks. If pi by t is less than omega, there is aliasing occurs. That is nothing but overlapping of these peaks, overlapping of the frequency spectrum. Okay, here aliasing occurs in the above diagram. We can prevent the aliasing error if the highest frequency component omega m in the signal x of t is less than or equal to pi by t, that is pi by t is greater than or equal to omega m, or omega m is less than or equal to pi by t. If it is less than omega m, then aliasing occurs. If it is greater than omega n, there is no aliasing occurs. If it is equal to omega n, highest frequency component omega n, then there is no aliasing occurs. Whenever the pi by t value is less than omega n, then only the aliasing occurs. We can prevent this aliasing error by using the or by changing the condition as pi by t is greater than or equal to omega m, or omega m is less than or equal to pi by t. Okay, if fs equal to 1 by t, sampling frequency is reciprocal of the time period, then phi fs is greater than or equal to omega. 1 by t is nothing but 1 by t is nothing but fs. So here replace this 1 by t by fs, then phi fs is greater than or equal to omega m, or phi fs is greater than or equal to omega m is nothing but 2 pi fm or 2 pi by t, right? So from this expression we can write fs is greater than or equal to 2 pi by pi, that is pi and pi gets cancelled, that is 2 fm. Fs is greater than or equal to 2 fm. That is considered as equation number 14. Equation number 14, right? So see here. So we can prevent the aliasing error by adjusting the condition phi by t is greater than or equal to fm. 1 by t is nothing but fs. So phi into fs is greater than or equal to omega n. But omega m is nothing but 2 pi into fm. So phi fs is greater than or equal to 2 pi into fs. Phi gets cancelled. So fs is greater than or equal to 2 fm. Okay, that is the condition of the sampling theorem. What is the condition of the sampling theorem? Sampling frequency fs is greater than or equal to 2 into fm, where fm is nothing but highest frequency component. Okay, and fs is nothing but sampling frequency. So the condition for the sampling theorem is fs is greater than or equal to 2 fm, double the highest frequency component. Fs sampling frequency is greater than or equal to double the highest frequency component, that is fs is greater than or equal to 2 fm. Fs is greater than or equal to 2 fm. Fs is greater than or equal to 2 fm, right? So now finally the sampling theorem is defined like this. A band limited signal x of t with x of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency, that is Fs, is greater than or equal to 2 Fm. Fm means highest frequency component. So that is sampling frequency must be at least twice the highest frequency present in the signal. That is the main condition of the sampling theorem. Okay, Fs is greater than or equal to 2 Fm, provided the signal is a band limited signal. X of t with x of j omega must be equal to 0, and here the condition is mod omega is greater than omega m. Okay, is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2 fm, that is twice the highest frequency present in the signal. Sampling frequency is greater than or equal to twice the highest frequency present in the signal. That is the definition of the sampling theorem. Okay, next coming to the Nyquist rate. What is meant by Nyquist rate? It is nothing but the minimum rate. Nyquist rate is nothing but a minimum rate. Okay, minimum possible rate at which a signal can be sampled and still be reconstructed from its samples. So with the minimum rate, a signal can be sampled and it can be reconstructed from its samples is called Nyquist rate. Okay, the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. It is always equal to 2 Fm. Okay, where Fm is maximum frequency component present in the signal. So Nyquist rate means Fm. Nyquist rate is equal to 2 into Fm, twice the highest frequency present in the signal. Okay, what is sampling period? What condition will indicate the sampling period, that is sampling frequency fs is greater than or equal to 2 into fm. What is Nyquist rate? Nyquist rate is nothing but 2 into fm. What is meant by Nyquist rate? It is the minimum rate at which a signal can be sampled and still be reconstructed from its samples. Okay, a signal can be sampled. So sampled means it can be converted into discrete time signal and it can be reconstructed from uh, that discrete time signal. It can be reconstructed as a original signal. Okay, original signal to discrete time signal and discrete time signal to original signal. Okay, so a signal can be sampled and still be reconstructed from its samples is called the Nyquist rate. It is the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate, which is equal to twice the maximum frequency component present in the signal, that is 2 Fm. So if here the condition, if a sampled signal at greater than Nyquist rate is said to be oversampled. If the signal samples at a higher Nyquist rate is said to be oversampled. A signal sampled at is less than Nyquist rate is called undersampled, and a signal samples at greater than Nyquist rate is said to be oversampled. Greater than Nyquist rate means greater than 2 Fm. Okay, greater than 2 Fm. Then that is called oversample. Less than 2 Fm, that is less than the Nyquist rate, is called undersample. Okay, so this is about the Nyquist rate. Okay, what is meant by Nyquist rate? It is the minimum rate at which the signal is sampled and still be reconstructed from its samples is called the Nyquist rate. It is always equal to 2 Fm. If it is greater than 2 Fm, it is called oversampled. If it is less than 2 Fm, then it is called undersampled. Okay, next coming to the anti-aliasing filter. Anti-aliasing filter. What is aliasing? Aliasing error means, so there is a overlapping of the frequency spectrum. Okay, that is called aliasing error. How to prevent this aliasing error? By adjusting the condition phi of t is less than less than or equal to is greater than or equal to fs. Okay, fm or omega m. Okay, pi by t is greater than or equal to omega m. So with that condition, we can prevent the aliasing error. Okay, we can also avoid this or prevent this aliasing error by using filters. We can use the filters here. So these are called anti-aliasing filter. Okay, a filter that is used to reject high frequency signals before it is sampled to reduce the aliasing is called an anti-aliasing filter. So how it is defined? Which is a filter that is used to reject high frequency signals before it is sampled. Used to reject the high frequency signals before it is sampled to reduce the aliasing is called an anti-aliasing filter. Anti-aliasing filter. So it is diagrammatically represented like this. So anti-aliasing filter is there. So x of t is the input signal. Okay. So it will give after filtering it will give x of n. Okay, anti-aliasing filter prior to sampler. Before the sampler we will introduce this anti-aliasing filter. That's why here the definition is telling that it is used to reject high frequency signals before it is sampled. Before it is sampled to reduce the aliasing is called an anti-aliasing filter. So it is used before the sampler. Okay, right? So that is called anti-aliasing filter. Next, we will discuss about the signal reconstruction. How the signal can be reconstructed. So here the original signal can be converted as the discrete time signal. From the discrete time signal, again we can reconstruct the signal, the original signal. Okay, right? So that we'll discuss in the next class, signal reconstruction and all these things we will discuss in next class. With this, I will conclude the today's session. Okay. So in the next class, we'll discuss about the signal reconstruction. Okay. Thank you.